The last thing I wanted to zoom into was this whole UUID business, because we kind of said it matter-of-factly during the creation of the student table, right? Unique identifier, easy peasy lemon squeezy. But what is a UUID even? Well, when we looked at UUID, we knew we had to create this extension, UUID OSSP, right? We need to install an extension, and this extension gives us the ability to generate unique identifiers. First of all, let's zoom into extensions. What are extensions? Well, extensions are pieces of software that allow you to expand what Postgres can do and expand how certain processes run. It basically expands your ability to do things in Postgres. And so if we look here, we have select from PG available extensions. This will give you the ability to look at all of the available extensions that came with Postgres. And UUID OSSP is one of them. UUID, what is it? Because we've seen that extensions are just those pieces of software that give us the ability to do these things. But what is a UUID? Well, with UUID, this extension in Postgres allows us to generate unique identifiers, and I've said it many times. Unique identifiers for primary keys. What does that unique identifier look like? UUID stands for Universally Unique Identifier. And what it basically does is it generates this random mishmash of stuff that's always going to be unique because it bases it off of multiple factors that are unique to generate something random. And over here, we can see what a UUID would look like. No one knows what exactly this means, but it's unique, and it will continue to be unique because it's generated based off of information that is unique at that moment. So you'll never have a conflict. You'll never have a conflict of an identifier. And so the question becomes like, well, Mo, why am I using this? Like, I see that it's unique and I see that it's useful and I see that, nothing's going to conflict with this, but why can't I just use a number from 1 to 100 and just go 1, 2, 3, 4, 5? Well, that's a good question. That goes into the question of like, why should I use them? What's the purpose? And the purpose is, again, this is another point of contention. Not everyone is a super fan of UUIDs. Everyone agrees that you should use them in some way, shape, or form because they're unique and they help you out in certain scenarios. But a lot of people advocate also for numbers that go from 1 to 100. And so UUIDs have a lot of pros and cons. Some of the pros are that they are unique everywhere. They're easier to shard, and sharding is one of these concepts that we haven't looked at because it's an extremely advanced concept that you use when your database is getting extremely large. Now, it also becomes easier to merge and replicate your data. Like if you're merging data, you want your identifiers to be unique. Could you imagine if you had two tables where you were using 1, 2, 3, 4, 5, 6, 7 as the ID, and then you had to merge it with a different table of information? Well, now you have two users that have the ID, the unique ID of one. How are you going to merge that? It becomes extremely complex. So using a UUID, you know that the IDs are going to be unique, that you're not going to clash on an ID. You could also easily replicate the data, create a replicate. One of the important last pros, and there are many other pros, but one of the most important last pros is that you expose less information about your system. If you expose that a user is 1, 2, 3, 4, or 5, 26 in your system, you're exposing some information about your system that you don't want people to know about. A unique identifier is way more pleasant in that regard. There are also cons to UUIDs. They're larger values to store. As you could see, it was a long string. It can have a performance impact because it stores more data, and it's way more difficult to debug. Like it's hard to go and look at a unique identifier and be like, oh yeah, it's that person or it's over there. Like they're just unreadable pieces of information that are unique. So UUIDs have their pros and cons. But at the end of the day, what we're aiming for here is to give you the concepts and the structures that are easiest and most commonly used. So where you can and where it seems valid, try to use UUIDs as much as possible for your primary keys. As a practice, it will make it easier for you, generally speaking, in the long run. When you get more seasoned and you see more types of data and you see more types of patterns, there may be specific use cases in which these just don't fit. These just don't work out for that particular pattern. But in general, and generally speaking, we want to give you the foundation that makes the most sense. So what makes the most sense, even though it costs more space to save, even though it can have a slight performance impact when you're talking about millions and millions and millions of records, the pros still outweigh the cons. So when you're starting off, use UUIDs for your primary keys as much as possible. And as you grow throughout your career and you see more and more patterns evolve and you see more and more different types of tables and different structures, there may be cases where you want an auto-incrementing number. You could even store one beside a UUID for easy indexing, for instance. There are many different reasons to use auto-incrementing numbers over UUIDs, but in general, I advocate to stick with UUIDs because they're unique and they're easy, and the pros outweigh the cons mostly. Hey everyone! Before we get into it, I wanted to dive into something called custom data types. Now, in this data model, we decided it would be good to show you how to create a custom data type. A custom data type being something that Postgres doesn't have out of the box. We looked at all of these data types, integers, floats, text, but what if you wanted to create your own? Well, what would that look like? And custom data types is something that you may come across depending on what databases you end up working with. And it's important to know, well, what they are and how they work. Now, you can go extremely complex when composing a custom data type, but for the purposes of this course, we wanted to go simple. And so what we decided to do was make a poor design choice. It's a poor design choice because it would have theoretically been better to model feedback in a way that was relational, aka having a table and properties like that. But for the intent and purpose of this course, we wanted to loop you through the thought process that can go into creating a model. And this model is by no means perfect. But in any given data model, poor decisions can be made. It happens. It just happens. Not every decision you make will scale properly or will be the best choice. And so in this model, we decided for a course, well, every course needs feedback. And for feedback, hey, let's create a custom data type that we're going to use the array syntax. So we're going to store multiple feedbacks directly against the course. Feedback will be a custom data type that will have a student ID, a rating, and feedback. And the rating will be a small integer that can range from 1 to 5. The student ID will be a UUID, and feedback will be text. And we'll show you how to do all of this. But remember, this particular custom data type isn't a good decision, but we'll get to that. Now, Postgres allows you to create custom data types to store shapes of data that are more complex. But not only that, it allows you to adjust and apply whatever you need in terms of a shape in order to get where you need to go. So with that said, we're going to create a custom data type here and we're going to show you how to work with it, but it's not particularly the best decision. Now let's go ahead and create that data type. So for this portion, we're going to go back to Valentina Studio. We've done the command line and it's great, but when writing queries, it really is beneficial to use something like full featured suite just because of all of the features it can give you: autocorrect, it can do autocomplete, it can do all of these different things. It can do formatting for you. So it's just a nicer environment and you can kind of go ahead and look into your schema and see what's available to you, what functions you have, all of that good stuff. So right now what we want to do is we want to create a type and we want to create the type feedback. And what we're going to do is we're going to say, hey, well, for feedback, I want a student ID because I need to keep track of that. And that's going to be of type UUID. And then I want a type of rating that's going to be a small int. Now, this small int doesn't really give you a check. And that check being like, well, what's my rating going to be? Is it going to be 1 to 5, 1 to 10? Small int can hold any given number. So here you have to make the decision whether your backend is going to do the check or the database. And that you could do this in a more complex way, create a domain, and a domain is just a specific type of data that can have a check. So we could have something like a rating here. Let's do that. Let's say, okay, create domain, and let's call it rating. Let's say that rating is of type small int. So we know that. and let's put a check on it, and let's say value has to be greater than 0 and value has to be smaller than or equal to 5. And so that way we know now that we have a domain of type rating. So last but not least, we need our actual feedback, and our feedback is going to be type text. So one more thing we need to do here before we execute this is we need to put as. And so what this basically will do is it will create a type that has a student ID of type UUID, a rating of the domain rating, and feedback of type text. And so don't get types and domains conflicted. A domain is nothing more than an alias for an existing type that can have a check constraint, a not null constraint. It can a default value. It's basically an alias for an existing type that can be a bit smarter than that existing type. And a type, a fully newly created type, acts as an independent type. So they're a bit different in that respect. And now that we have this, we know that our rating has to be between 0 and 5. We know that our feedback is text, and we know that our student ID has to be a UUID. And so now that we have a custom data type, and now that we have a custom domain, which is nothing more than an alias, we can go ahead and we can create the rest of our tables based on what we see here. So we've just created this part over here, feedback, which is the custom data type of UUID. And we even went so far as to create a small int alias called a rating that can go from 0 to 5. So with all of that, we have our custom feedback type ready to be used in the course table. And let's go ahead and create our tables now. Here we go. We're going to create all of these tables in one fell swoop. We've already created this custom data type behind the scenes, and we've adjusted the rating to be of type domain, which is an alias type that can have a constraint. So we've already set this up. Now it's time to set the rest up. And so we're going to start off with student. And as you can see, a student can belong to one or multiple enrollments, but an enrollment can only belong to one student. Sorry, that's 0 or more enrollments. But an enrollment can only belong to one student. So when we set up a student, what you can see here is that because the student is on this side of the relationship, it doesn't really have any bearing on the student, the enrollment, but the enrollment needs to know about the student. So we can pretty much set up this table without having to take into account any foreign keys. And as you can see here, I've taken the liberty of telling you which parts should be the primary key. Now, throughout this video, feel free to pause the video and try out the create table statement on your own, and then come back to the video and see how we apply the create table statement and how closely you align to that. So let's go ahead and create student. And so over here, we're back in Valentina Studio. And what we can see here is that if we do a create table, what we're going to see is that we can apply student. And then what we need to do now is we need to define the columns that go in here. So we say student ID, the ID of the student is of type UUID, and we're going to say default, and we're going to say UUID generate v4. That's the one we need. And we're also going to say that this needs to be the primary key as the constraint. So let's put primary key here. So we have a constraint, we have a default value, and we have a type. Okay, then we have first name. And this was of varchar, and we need to give it 255. And last name is the same. It's varchar 255. And then the last property we had was date of birth. And this one we want to give type date. And so we could give these individual constraints, and we can say here, you know, this can't be null, and this can't be null, and this can't be null. So none of it can be null. And so if we go ahead and execute that statement, and we go back to our schema editor, and we go to the tables overview, and we quickly refresh this, we can see that we have a student now with a student ID that has a primary key, first name, last name, and date of birth. Awesome. So now that we have that, what we want to do next is we want to create our following table, right? So let's go over to enrollment. Oh, wait, enrollment needs a course ID as a foreign key. So if it has two relationships, well, let's go ahead and create course first. But course also needs a foreign key to teacher and student. Okay, so let's isolate the tables that we can make the easiest. So subject has no relationship. So let's go ahead and create subject. And so we'll go ahead and create table subject. And what we'll give it is a subject ID of type UUID. And we'll say it's the primary key. And we'll default it. And we'll say UUID generate v4. That's the one we need. And then we'll give it a subject of type text. And we'll say not null. And we'll give it a description of type text. But this is optional. So did we get that right? Yep. Seems like we did. Subject is of type text. Description is of type text. This is optional. We added the constraint not null to this. And so we could have put the constraints visually inside of this diagram as well. I just chose not to keep it as simple as possible. And so if we create this table and we go over here to our schema editor and we refresh our schema again, we can see that we have a subject and we have all of that good stuff. All right, 2 tables down, 3 to go. So now that we've isolated the 2 tables here that didn't need any foreign key relationships, well, let's go to the third one, teacher. All right, so teacher has a teacher ID, first name, last name, email, and date of birth. And it seems like we forgot the email on the student. So I'm gonna have to show you how to add that after the fact. So let's go ahead and create the teacher. Create table teacher. And let's give it a teacher ID. Again, UUID, primary key, and let's default it to UUID generate v4. And now that we have that, the next part of this is the first name, which is a varchar of 255. And let's give it a not null. And then let's copy that. Let's paste it. A little lazy. Last name. Same deal. Date of birth is of type date. Let's give that a not null. And then let's say email is of type text. Now we did show you how to do the constraint on the value, the check constraint to check the email validation. For all intents and purposes, I'm going to leave that alone for now. And let's execute that teacher creation. And we can also just quickly over here do a refresh, and we'll see that we have 3 tables now, teacher, subject, and student. And we did see that we forgot a field on student, so let's go ahead and alter that table. An alter table is a way to change tables that already exist. And so what we want to do now is we want to alter the table student, and we want to do an add column, and we want to do email of type text. And once we execute that, what we'll see here is that our student didn't have the field. But let's go ahead and refresh this. And suddenly it has a 5th field, email. So we're good now. Happens, you can forget a field here or there. So now that we have teacher, student, subject, let's go ahead and create our course. So create table course. And this one is interesting, right? Because this one has foreign keys, it has a primary key, it has some text, it has a custom data field, it has all the fun stuff. So let's go ahead and let's put in course ID, and let's give it UUID, primary key, all the good stuff, default, UUID generate v4, so that we don't have to worry about generating a value for it. And then we'll give it a course name and description of type text. So let's say name. Oh, name is a reserved keyword, so let's put name. And then let's say text. And then what we need to do now is say not null. We want to give that constraint. We want to give it a description. And so description is of type text. We'll optionally leave that empty. And so now we get to the fun stuff, subject ID and teacher ID. So let's put them in here, subject ID, teacher ID. And so now we have to do a foreign key reference. So we say reference is subject ID. And here we say references teacher ID. And so with that, we now have created our foreign key relationships. Now, interestingly enough, let's see what happens when we do this. And let's add feedback as well. So feedback, our type feedback, and it's of an array type. As you can see here, our type feedback got lowercase because we didn't use the double quotes to uppercase it to feedback. Always good to remember to use these when you want to do case sensitivity. So we're going to do feedback of type feedback, and let's create that table. Interestingly enough, it seems I've made a mistake here. And what it seems I did was I forgot to give it a type. So subject ID is of type UUID and teacher ID is of type UUID. And so when we execute that, what we'll see happen here now is if we refresh this real quick, we're going to see an extra table, and we're going to see the table course. And if we open up the fields, we'll see course ID, subject ID, teacher ID. Now comes the last part, the enrollment. So let's go ahead and create the enrollment. And what we need to do here is we need to give it a course ID, a student ID. And so let's do UUID, and let's say references course ID. And here this references student ID. And then what else do we need here? Well, of course, we need an enrollment date. So let's put that. Let's say date. Let's say not null. And then one more thing we need is a primary key, because we didn't have one here. Because we have two foreign keys here, what we can do is we can combine them and say the primary key is course ID and student ID. And let's go ahead and name this constraint primary key enrollment. And let's execute this. And so now that we've executed this, what we'll see here is if we do a refresh on this, what we can see is if we go into enrollment and we open our fields, course and student ID are the primary key. And we can see that because they both have a key symbol beside them. And so with all of this, what we've ended up creating is the entirety of this here data model. Now this data model is by no means perfect, but we can start putting data into this data model, and we can start creating an environment in which we have more and more to work with. And with that, we may uncover some of the flaws that can come with a data model. No data model is perfect. Every data model can have flaws. And by putting data into the model, we may uncover some of these flaws and change the model perhaps, as many data models change over time because the needs change or the model isn't progressive enough to handle future-proofing itself. So let's take a look at inserting the data into the tables. We created our entire data model. We've created a student, an enrollment, a course, a subject, a teacher. We've even created a custom data type called feedback. But now comes the interesting part. Because we put together our entire model and we have everything ready to receive data, but we don't have data just yet. And so you may ask yourself, well, in what order, what fashion do I go ahead and create data? Well, that's very dependent on the user journey, because not often will you be creating data on the database layer specifically for what would be considered a user journey. If we were to apply the ZTM database to an actual platform, well, a student would go ahead and register themselves, and a teacher would go ahead and register themselves, and then a teacher would go and create a course, and there would be a course creation flow, and then a student would go and buy a course and thus be enrolled into that course. And because they get an enrollment by buying that course, so the whole flow goes. And when a student buys a course and is enrolled in the course, they can submit feedback eventually to that course. Now, with all of that said, we're going to learn how to insert data at the database layer. But that is not necessarily representative of a user journey or an actual flow. It's just a way of manipulating and injecting data into your environment. Let's start off by creating a student. So over here, we are in Valentina Studio yet again, and we're in the ZTM database. And as you can see here, we have all of our tables ready. And we have a student object, and we can see the fields that it needs to accept. So what we want to do is we want to insert into. This is the command that we will use to insert data. And we want to insert into student because that's the table that is going to receive our values. The following part are the parentheses that follow. And this will determine in what order you want to inject data. If you do not tell it which order, it's going to accept the order in which the fields are injected into the actual table. And so how would we see what that looks like? Well, we would go over to our schema editor and we would open up student, and what we would see is that it accepts student ID, then first name, then last name, then date of birth, then email. So it's according to the order in which we added them when we created the table. It's not according to the order in which the data editor is showing us the fields, because it's showing us them alphabetically. So it's always useful to tell the insert statement in which order it should receive it. So let's do student ID first. Well, oh wait, didn't we say that student ID had a default value? Silly me, we don't need to actually inject anything into there. So that's also a big plus of telling it specifically what fields you want to populate. So let's populate first name, last name, email, and date of birth. And by doing this, what we're going to enable ourselves to do is inject values. And the values we're going to inject are, well, Mo, last name Beanie, email mo@beanie.io, and then, well, my date of birth. Well, we've seen how to do this. We can fill it in different ways and format it, but let's start year, month, day, because that's the easiest, and then let's convert this to a date with our conversion operator. Awesome. So if we go ahead and execute this, what we're going to see is that we've inserted info into student. And if we go ahead to student enrollment and we refresh by pressing Command R or Control R, depending on what environment you're on, we can see that a student ID was automatically generated. So we automatically have our primary key by using that default keyword. And first name, last name, and date of birth and email have been filled in. So we have our very first student. All right, let's go ahead and create a teacher. And teacher accepts almost the same things. Now, here's the thing. A student can also be a teacher. So theoretically, I can inject or insert the exact same information. Well, let's go ahead and do that for simplicity's sake. And by inserting this into the teacher, what we can see now is that if I opened up the teacher, well, Mo's also a teacher, but it's a separate entity. It would almost be like considering it a separate person. We don't have the concept of a user. The first flaw in this data model is that we completely separated the concept of a teacher and a student, but we don't have a holistic user to which we could give quote unquote a role, not a Postgres role, not a database role, but if we were to model a database, we would be able to give them the role of a teacher and the role of a student, and they could be both at the same time. Now they're completely separate entities. And so our system would already fail at this level because, well, how are you going to let them log in? What if they want to be a teacher and a student? How is that going to work? And so this model is already exploding outwards. So how would we solve for this? We could maybe create a user table over here, and we could have a user ID, and then a student, instead of having a first name, last name, date of birth, we don't need to keep track of this potentially. We could just give them an is student flag or an is teacher flag. Wouldn't that even be better? And then everyone by default that registers is considered a student, but being a teacher is opting in. That would be interesting. Now, of course, you can expand the data model and make it easier, because the way that we structured this, we weren't really thinking of the end system and the end user. We just went ahead and we said, well, we have a teacher and we have a student, and let's go model those. But we really didn't think of our end system and how this scales. So now we could see that, well, Mo can be a teacher, but Mo can also be a student. But how is the system going to handle that if we were to build something eventually? It's going to be very difficult, because Mo the student and Mo the teacher, although they have unique IDs, they're theoretically the same email address. By using the same email address, well, how are they going to log in? We could make them log in by teacher ID, but that teacher ID is jarbled. We could give the teacher a username and the student a username, but that's also jarbled. So you can already see by us explaining and going through this exercise of inserting data, we're already seeing flaws in some of the parts of our data model for expanding it outwards. And with every data model, there comes a point where there are certain flaws in the data model that need to be addressed. Now, this specific data model issue we could address, but it's much easier to trek forward with the data model we have and explain all of the different concepts around updating, deleting, inserting, instead of creating the most robust model up front. This is, of course, an educational course. When we get to database design, that's when we'll look at all of the different ways that we can look at designing a system. Because that is, again, a very, very different skill set. And you're never going to get it right on the first go. Designing a system, designing a database is a very hard task. And just rudimentarily creating this data schema that seemingly covers all the bases can already show flaws in an end system. Now, let's go ahead and create a course. Next up, we're going to make our very first course. We're going to have a course with a name, a description, a subject. We're even going to give it a teacher, and maybe eventually some feedback. So over here, you can see that before we create our course, we may need a subject. So let's go ahead and create a subject first. So again, we're going to insert into subject, and we already know that our subject ID is going to have a value defaulted into it. So let's give it a subject and a description, and then let's say values, and then let's go ahead and let's say, well, let's call it SQL 0 to Mastery. Just a simple course name, nothing to do with this course at all, just what came to mind. And let's call it the Art of SQL Mastery. Again, nothing to do with this course at all. It has no bearing. I wasn't thinking of this course at all. It just random thing that came to mind. And so when we execute this, well, what we're going to see is that, is this actually a subject? Huh. Oh, I mixed it up. This is what I actually wanted to give my course name. This is the course name I wanted to give, and this is the description of the course. I accidentally inserted it into subject. Well, stupid me. We can go ahead and we could delete that. So let's do a delete from subject, where, let's say, where the subject is equal to this. We could also go ahead and find the ID and do it that way, but it's a whole thing. If we did this, let's go see what's in our subject. CTM, public, subject. And nothing in here. Let's just confirm that we actually deleted it, right? Like, I did it, but I didn't really show you if it was there or not. So if we execute this and we go over here, we can see, yeah, SQL 0 to Mastery, the Art of SQL Mastery. Well, that's not really a subject, is it? So, we went ahead and we used the delete from syntax. So we delete from a table. And then with the where clause, we can go ahead and we could write a query. We could write a simple comparison. It's basically the where clause that we're used to from our SQL queries. And this is what gives us a lot of power. I didn't even have to check here on the ID. I could just say where it's equal to this. So, if we execute that, again, no more course, no more subject. So that little mistake, easily rectified. What do we actually want to inject in here? Well, as a subject, we wanted to inject SQL. And then as a description, we wanted to inject a database management language. So let's execute that, and in subject, we can see, okay, we have our SQL as a subject. Okay, now let's go and insert into course. What do we have in course? Well, that's where this comes in handy, because I can just quickly go check the fields, and we can see that we need to give it a name. And let's just make sure that we do that correctly. We can give it a description. Here's where we need to make a decision. So how does feedback work? Well, feedback is something that's given by the student. So we're not going to inject it while we're doing the course. That's not how it would work in a real system. You're not going to inject a course and then inject a bunch of feedback into it unless you're doing a migration from an existing system. Feedback is something organic. Feedback is something that the student gives. So it would usually be an update command. You would be inserting a value or updating a record and then inserting a value into that feedback array that we have. So we're not going to give it feedback right now, but we may need to give it a subject ID and we may need to give it a teacher ID. Let's go ahead and just create our course for now. Normally a course is created by a teacher, so we would need the teacher ID, but let's go ahead and say, all right, let's call it SQL 0 to mastery. Let's boost it up a little. The number one resource for SQL mastery. Easy. This has nothing to do with this course. I'm not thinking about this course. It's, purely hypothetical. So let's go ahead and create that course. And what we can see now is if we went ahead and we went to look at our course, well, hey, we were allowed to create a course, but we didn't have to give it a teacher ID and we didn't have to give it a subject ID. Interesting. So when we created our foreign key reference, we didn't actually tell it that it had to enforce it. So it's allowed to be null. Well, we don't want that, do we? We want our table to we need a teacher. A teacher for sure has to make a course. And, every course needs a subject. You can't have a course without a subject. So how are we going to do that? Well, silly me. I forgot to actually give it the proper constraints. So we're going to do an alter table, right? And what we're going to do is we're going to alter the table course. Well, if we go ahead and alter the table course, what we want to do is we want to alter the column subject ID, and we want to set not null. And so the first thing we see here is subject ID contains null values. So before we can even alter it, we would need to delete our existing course. Well, that's not good. So how would we go about that? And so technically what we're looking at here is a mini migration scenario, because we can't just go ahead and alter the table to set the subject ID to not null, because we have a course that doesn't have a subject ID. And because we have a course that doesn't have a subject ID, well, what we now need to do is we need to fill in the gaps. We need to fill in the gaps before we alter the table, because we can't just go ahead and alter the table. We need to maintain the integrity. So how would you go about that? Well, if you were looking at this from a migration perspective, what you would go and do is you would potentially maybe create a subject that has a specific subject that would flag other systems to say, hey, this user needs to add subjects. Null is not an allowed value. But now we need to give it a subject ID that references a primary key over here. So we would go and create a subject that is, quote unquote, a fake subject. And then if you have that fake subject, well, now the other systems can be like, they have this fake subject, so we need to tell them to select a different one. So that's how you could progressively migrate, for instance. Many, many different strategies can go in here. This is just one, very simple one. That said, what we need to do basically is we need to go and update the courses and fill in a subject ID before we go ahead and migrate. And we only have one subject. We could go ahead and do all of this stuff, but let's just give it the subject we have because we're in a very simple state. So how do we do that? Well, we would go over here and let's forego our alter table for now. Let's do an update statement. So update statements work like this. You update the table course, and then you have the option to set something. So we'll set subject ID, and we can set it to whatever we want. So let's go over here to our courses subject, and let's copy the subject ID. And we're going to set the subject IDs to SQL, but we're going to do it specifically in specific scenarios. So we're going to say where subject ID is null. Otherwise, we would do it everywhere. So if we run this, what we're going to do is we're going to see now, if we refresh here, well, now we have a subject ID. Okay, awesome. That means that we can go ahead and we can run this alter table, right? And if we run this alter table, oh, no issues. And now if I were to say insert into course, and we said that we were going to insert just a name and a description, well, what's going to happen now is we're going to get an issue, name and then description, just to give an example. And we did this. Well, okay, name and description are mandatory. Course ID is going to be generated, but what's going to happen here is we're going to get an error. Null value in column subject ID value is not null constraint, so we cannot add a course without a subject anymore. And the same should be true for a teacher ID. So if we do alter table course, well, what we want to do now is we want to be able to set that teacher ID to also not be null. So let's go ahead and let's alter the column, and let's say teacher ID, and let's say set not null. Now, what's going to happen is, oh, teacher ID contains null values, so we have to do an update statement here. So what we're going to do is we're going to update course, and we're going to set teacher ID, and we're going to have to set it to a value where teacher ID is null. And this one would be a more complicated migration, right? Because if you have a bunch of courses that don't have a teacher, well, what are you going to do with them? Well, you can't just go and sunset them. They probably have course material, although maybe they're owned by the system at this point. So you would maybe create a teacher called system, and it would just be owned by the system, not a specific teacher, or you would probably sunset them. Who's to say? It really depends. Now we need to figure out a teacher ID. So let's go to teacher. Let's copy Mo's ID. And I know this is going to be funny. Mo's going to be teaching Mo. In any case, we'll set the teacher ID where teacher ID is null. And then when we go over here, over to the course, what we'll see is that we have a subject ID and we have a teacher ID. We have no feedback yet, but feedback is an organic thing. We don't have feedback. So, but now what we need to do is we need to do the same alter table again, and we need to set the teacher ID to not be null. And from now moving forward, you cannot create courses without giving it a teacher ID. And so now you can kind of see why it is very, very important to put the right constraints in place and to think about the constraints of your system. This is more about system modeling than it is about specifically the database commands and queries. You have to put a lot of forethought into what exactly you're going to build before you go ahead and create this model. And even when you create this model, you can make mistakes and you may need to alter some things. And these alter commands and these update commands, they're very useful in your toolkit to be able to go ahead and alter certain things, migrate certain things, make sure that everything is in a good state so that you can make the data your own. Because once you create this database and once you put it into production and once you have all of your data, well, that's when it becomes very, very hard to do these migrations. That's why systems go into maintenance mode, because when you touch the data behind the scenes, well, you don't want clients and software injecting data into your system while you're trying to migrate to a completely different schematic. If we, for instance, said altered teacher ID's name or feedback to a different type or whatnot, all of that stuff, you would have to put the systems that are trying to talk to you into maintenance mode. You'd have to put them to sleep because you don't want systems touching your data while you're changing things. So once you put this out there, it's very important that you're 100% certain of your model and that you test it and that you validate it. And that's what the software development lifecycle is for. Databases and database engineers have to live very closely to the developers in order to make sure that everything that they're putting together and that the system design is coherent. The final thing left to do is enroll a student into a course. We've basically set it all up. Okay, we don't have a ton of data, nor do we have a ton of things set up in the best way. This model is very, very simple, but it's very, very effective at teaching the absolute basic necessities of these commands and where and when to place them. Because at the end of the day, when we write queries, what we're trying to accomplish is fetching data. That data shape, that model, is extremely important in the way that you're going to interact with that data. Looking at how we have to shift and make that model more malleable and better towards those outcomes is extremely important. So with that being said, well, let's go ahead and enroll a student into a course. And what we can see here is that we need a course ID, a student ID, and an enrollment date. So if we went to say insert into enrollment, we need a student ID, we need a course ID, and we need an enrollment date. Well, on this table, we also didn't put any foreign key validations. Not at all, actually. We didn't put any not null checks on any foreign keys. So that was our first mistake. But if we insert the values into here, what we need is we need the student ID. So if we go here, and we quickly do this, we can get the student ID, and we'll just fill that in here. And then let's go into course ID, and let's go into course. And there we go. And then as last thing, we need an enrollment date. So let's put now, and let's convert that to a date. And let's execute this. And there we go. We have now enrolled a student into our course. So if we go into enrollment, our student is enrolled into the course today. So we've done a full, so to speak, flow of what a user journey would look like if there was an actual website or app backing this thing, and we did it in the right steps. One other thing we need to do is, well, the student is going to go through the course. And once the student goes through the course, what needs to happen is feedback needs to be given. So let's look at how we would give feedback. So obviously now that we're going to add some feedback to a course, we need to do some kind of update command because we're going to update this existing course with SQL 0 to Mastery with some feedback. And so I've put together this update command that we're going to run through. And what this update command is basically doing is saying it's going to update the course table. And we're going to set feedback, and we're going to array append. So now that we're working with arrays, we have a feedback array. And we have to append to that array. We're going to add something to that array. To this, you could also do array.delete. You could delete something off of an array, or array remove, I believe it is. Let's take a look. Array remove. You could replace, and so forth and so forward. But we're going to append right now. And what we're going to do is to the feedback array, the existing array, we're going to append a row. Now, this is the syntax you can use to define a custom row of any specific type that you will append to an array. So with row, what we can say is, well, we have the student ID, we have our score, which is a 5, and we have our feedback, which is great course. Now that we have this, we're going to cast it to the type feedback. And we're going to say, hey, do it where the course ID is equal to this course ID. And this is exactly how a potential backend system would formulate a query to insert feedback into this array. It would just append it to the array. We don't want to go ahead and do kind of deletions and stuff like that. That would be more complex. We could potentially do a deletion where the row is equal to the student ID. A student could potentially leave multiple feedbacks. We don't know. There are really no rules around this custom type since it's just an array. You can just keep putting stuff into the box. There's no real constraints, and that's one of the downfalls of this type. So when we append to this array, when we do this, and we execute this, what we're going to see is we've inserted successfully into this course a feedback. And if we go see here, we can see that if we refresh here, we now have our feedback. And our feedback is an element on the array. So knowing this, well, we can now start adding feedback to the array. But one of the downfalls of this is I could do whatever I want here. I could do PE74. I could do, interesting, PE is invalid syntax for a UUID. So let's do something like FC73, and let's do something like DC73, and let's do something like 4571, and we can change whatever we want as long as we fall within the proper ranges of a UUID, which is A to F. What I'm basically showcasing here is I could generate whatever I want here. It doesn't really matter. It's not going to check if this student ID exists. And sure, I'm getting a lot of 5 stars, but I can't verify from who they are. And that's one of the other drawbacks. I'm storing all of this feedback, but the shape that I'm storing it in really isn't the most ideal shape, right? Like I have this box of feedback, and of course it can hold all of this information, but it really isn't the most ideal. And you can see now the query has to be more complex. I have to do an update instead of an insert, and I have to update the course information every time. I don't want to be updating my course every time. I want to insert feedback somewhere, and I want to keep it separate from the course. There are more efficient ways of doing this. And as this array grows, like we don't have any integrity checks. We have to do this complex mechanism of generating a row and converting it. Like the query is immensely complex for what it's giving us right now. So how would we go about fixing this? Well, we would need to change the data type that we have here. We would need to change the model. And so let's go look at what that would look like. So you may be asking yourself, well, how are we going to change this in order to accommodate feedback from multiple students and to a course? Well, to do that, we need to change our custom data type into something completely different. We need to shape it into a table. And the reason we're going to shape it into the table is because when we use tables, we can follow the relational model. And what does the relational model warrant? Primary key, foreign key interaction, constraints, checks. There's so much more you can do with tables than you can do with custom data types. Custom data types don't allow you to do complex checks, foreign key references, all of that good stuff. And then on top of that, arrays add this complexity onto any data shape and query you're trying to write. Could you imagine having to query the arrays and do complex calculations against each individual? Well, you're going to have to write array iterations and all of this stuff. And it doesn't make sense for what we're trying to accomplish. It doesn't make sense in terms of the data shape. The data shape needs too much love. And what I mean by love is we want to query that data a lot. It's something very important. Feedback is something very important. So to demote it almost to a data shape instead of a table is kind of offensive to feedback. But that doesn't mean that there aren't good cases, for instance, custom data shapes. For instance, a phone number. A phone number could easily be an array because you may have multiple phone numbers, and you may have multiple phone numbers for your home, your cell phone, and all of that good stuff. And you may want to store a custom data shape for that. That already sounds like a way better use case. Feedback is just too important to us. So as you can see here, what we did is we changed our custom data shape. And what we did was we made it a relationship. Each individual feedback can belong to one student, but a student can leave multiple feedback, right? So a student can leave multiple feedback, and feedback belongs to one course, but a course can have multiple feedback. So one individual feedback has to belong to a certain course and a certain student, but students and courses can have multiple feedbacks. So it's kind of an interesting way of shaping this relationship. What you can see here is that we have a student ID and a course ID as foreign keys. And I've highlighted them as potentially being the primary key, but let's look at that. Let's look at potentially making the combination of these two the primary key. First and foremost, what we have to do is we got to go change what we already put in place. We have a custom data type and we have a domain for the rating that is rating, and it's of type small int, and it has a range and all that stuff. We have to change everything. And this is potentially a scenario where you would get into a migration of the existing shape and taking that array and taking the values of each individual part of that array and putting it into the new feedback table. Now, since we only have one feedback within that array, we're not going to go into a migration scenario. What we are going to do is we're going to create a new table. So we're going to do create table feedback. And what we're going to do is we're going to give it the student ID. We're going to give it the course ID. Okay, so these are the two things that we knew were going to be UUIDs, right? They're both UUID. And both of them are foreign keys, so they're going to reference. So this references student ID, and this references course ID. All right. So knowing that a feedback is the sum of these two, this is the unique relationship. We know that these together should be the primary key. Now we can't give them the primary key on this particular key, but in order to make them the primary key, we also have to make sure that they are not null, right? We don't want that. All right, so then we have our feedback, which is of type text. And then as final thing that we needed to do was rating. And that was of type rating. Okay, so knowing that, now we need to do the constraint. So let's do constraint primary key feedback. And let's say that it refers to student ID and course ID. The combination of these two is the primary key. All right, so what's going to happen when we execute this query? Any guesses? It's going to fail. Well, it failed for a different reason. I forgot to add the primary key, lol. But when we execute this, what it's basically going to say is, hey, you already have a feedback. Interesting. Our type feedback is conflicting with the table feedback because they're both objects in the database and they can't just have the same name. So what we need to do here, and I could go and alter the name through a query command, but let's use the niceties of Valentina to quickly change this. And if we go into design on feedback by right clicking, we could do feedback deprecated. And once we apply these changes, what's going to happen is once we refresh here and we go into the course table and we press design here, what we're going to see is if we look at the fields, we're going to have feedback and it's of type public feedback deprecated. So it's already cascaded through the system. And the one more thing we want to do, let's also call this feedback deprecated, this field, because this is our deprecated feedback. We're not going to use this anymore. We may want to query it at some point, but we don't need it, right? It's gone. We might as well even delete it, but let's just keep it there for now. So now we have our create table here. And what happens if we execute it now? Well, it executes successfully. Shocker, we don't have a conflicting element. If we refresh here again, then we can see that we have our feedback now, and it has 4 fields, and the student ID and the course ID are our primary keys. So how do we go about inserting data into this now? Well, if we do insert into feedback, we have a very different experience. So now we have to say, okay, well, the course ID and the UUID aren't going to be given to us, so we need to give it to them. We have student ID, course ID, feedback, and rating. So those are the 4 things we need to give to it. And we're going to give them in this order. And we're going to say values. So how are we going to get our values? Well, we need to get a course. So let's go and see. Let's open the data editor. We have a course. Got it. So we have a course ID. Where was our course ID? It was a second value. So in the second value, we're going to put this. Great. In the first value, we need a student ID. So let's go ahead and get ourselves a student. And let's open the data editor here. And we got ourselves a student ID. So that goes into the first value. And then we need to give ourselves some feedback. Well, this was great. And then we need to give ourselves a rating. And that could be from 0 to 5. Let's give ourselves a rating of 1,000 or 100,000 or whatever. And let's see what happens. Well, that's going to fail because the small int is out of range. We said it had to be from 0 to 5. So let's give ourselves a 5. Let's give ourselves a 4. So let's execute that, and we've inserted. So now if we go look at feedback and we open the data editor, we now have feedback from this student on this course, and the feedback, well, this was great, and the rating was a 4. And so now we can query this actively. We can query this in a smart way. We don't have to go out of our way to use array syntax to kind of mangle this stuff and write custom select and update queries and all that stuff. We can just insert, and we have a relationship and we have integrity. I can't just go ahead and say, do F2 and 7664 here. Whatever the case is, it's going to error because there's a foreign key constraint. So we have safety. It's great. Overall, it's great. That's why we use the relational model. And that's why the relational model is so great. All of these constraints, these checks, these data integrity, we got it on lock. And of course, custom data types still have their place. They're not a bad thing, but you can make bad decisions with them. And that's what we're trying to highlight here. So with our feedback table, all here, we could basically add data to this as we go. And there are 100 different customizations we could make to this data model to make it more robust, more applicable to current software needs, and so forward and so forth. But with this, we basically have successfully created a solid base for a good data model to write queries against and learn and insert data into and try things out. We've been from A to Z. We've seen everything from basic SQL commands to database commands to role management and everything in between. And now that we know how to create a database, and now that we know how to query a database and manage a database and all of these good things, well, we have to prepare for the worst case. And so that's why I want to talk about backups. Backups are so important. You may ask why. We all know backups are important. Generally speaking, the majority of the population doesn't even take backups of their personal stuff, but when you're managing databases and when you're doing this as a profession, safety first. That's what I preach. Safety first. Because disaster will strike. You will hit a scenario where something unexpected happens. You may not know what it is, and it depends very much on the scenario you're working in. Are your databases in the cloud? Are they on-premise? Do you have your own hardware? What's going on? All of these different aspects play a part in how you're going to manage this. You may ask yourself, okay, Mo, I get it. We know how to create a database. We know how to manage. We know how to do all of this stuff. And, backups are fairly easy. We can just take a full backup of our Postgres database. And yeah, you can. You definitely can. But as with everything else, when disaster strikes, when unexpected things happen, we need to have a strategy in place. And that strategy can be complex. It can be simple. It really depends on the size, the complexity. All of these things play a role. And so what we want to do here is we want to show you some of the ways that you can go about formulating a strategy around your backups, because there are many, many different ways of going about this. And it's just important that we run through it. So it's important. That's what we're getting at. It's important. Backups are vital to a system, and especially when we're talking about databases. When we're talking about databases, it's so important because this is the data. This is the crux of the company. How you store and manage your data is important. And we can't stress this enough. We can't stress this enough because something will happen. And it's important that you're in the right position, that you know the right techniques, the right way of going about it in order to manage the situation correctly. Now, what we're going to do is we're going to make sure that you have a plan. There are many, many different tools. There are many, many different ways of going about backups. But the essence of it all is that you have a plan, that you are this happy apple over here. Now, there are 3 things you need when you're thinking about backups. You need to have a backup plan. How am I going to make the backups? What type of backups am I going to make? Why am I going to make these backups? All these questions need to be answered. Then you need a disaster recovery plan. When things go wrong, people underestimate how important it is to have an operation in place. When things happen, okay, you may have your backups. You may have them all in place and all of that stuff may be taken care of. But what's most important is that, well, when things like this happen, how are we going to handle it? If a database goes down, well, how are the applications going to react? Are we just going to allow them to continue operating, or are they going to poll for a health check, for instance, just a simple health check? And will they go into a quote-unquote maintenance mode? The disaster recovery plan tells you exactly, okay, a database went down, what are we going to do? The applications go into maintenance mode. Everything is basically put to a stop, a halt. And these are the procedures we're going to follow. From the first hour, we're going to assess what exactly happened and why it happened. The second hour, we're going to start putting in place the backups and the recovery procedures in place. The third hour, we're going to give a status report. This disaster recovery plan tells you exactly how you're supposed to operate when things go wrong. And putting in place the disaster recovery plan is extremely important. There's many different ways of putting this in place, but what we want to do is we want to tell you, hey, these are the things you may want to think about. And then you can go ahead and try to draft a way around it, because it's important to know how to operate when things go wrong. And then the third and most important thing is when you put in place these plans, well, test them out. Always test out your plans, because you never know, is my disaster recovery plan going to work? Are all systems a go? Does my backup plan have all of the different pieces it needs in place? You need to test these things out, because if things actually happen and you can't follow your procedure to a T and there's some kind of hiccup, well, that's going to cost you time. And more importantly, that's going to cost your company a lot of money. What we don't want to do is incur revenue loss, because at the end of the day, we're operating a business, and determining what the importance is of our data is determining what the importance it is to the company. And data is one of those cruxes of any given company. You really have to have this in place, and you have to think about this. Now, you may be asking yourself, what can go wrong? If we're in the cloud, if we're on AWS or Google Cloud or all of these things, they handle it for us. Yeah, those are different scenarios. You may end up in a place where everything is on premise, meaning they have their own hardware, they have their own servers. And even when you're in the cloud, you need to think about your backup strategy. You can rely on these cloud services to have sane defaults, but you still need to think about these things. So what can go wrong? And these aren't all applicable to cloud versus on-premise. We took this from the most raw approach, which is you are the owner of your database, you are the owner of your data, and you are the owner of the hardware. Well, given those parameters, what could go wrong? Well, your hardware could fail. Your hard drive could be 5 years old, 6 years old, have a lot of reads and writes, just one day decide, you know what? I'm done. I'm going to sleep. And suddenly, with a hardware failure, well, what are we going to do? We have to swap out the hard drive. And there are many different layers that you could go here in terms of hardware redundancy failure, some kind of recovery plan when you swap out a hard drive. There are many different ways of doing this. RAID, R-A-I-D, is one way, a redundant array of disks. And the disks will basically hold some kind of copy of each other so that when you swap out disks, there's some kind of fault tolerance at the hardware level. Viruses, understated problem, but they can happen. You can get a virus on your system. It can wreak havoc. And what you have to do then, you may have to reinstall the operating system. You may have to flesh out you may even have to go across systems. It could infect multiple computers. Power outages, also a very understated problem. Now, when power outages happen, if you're on premise, you have to make sure that you have some kind of backup generator that's going to power your servers as the power goes out. Because hardware failures usually, if not most of the time, will probably come from a power outage of some sort. Power outages, short circuiting of components. We're working with very fragile material at the end of the day. We don't really think about it that much, but hardware is very fragile. And we have to take that very seriously. So with power outages, one strategy, have a backup generator. Hackers, another understated problem. If Twitter can get hacked and Instagram can get hacked and all of these services that seemingly have impenetrable security analysis, they pay through the nose, yet hackers get through. Don't underestimate hackers. Where there's a will, there is a way. So make sure that you have redundancy and safety, because when hackers come in, they can do whatever they want. And then there's human error. You may do something wrong. You may run a wrong query. You may accidentally delete a bunch of records. It can happen. And there's many, many more reasons that things can go wrong. These are only 5 of a list of potential hundreds of things that may end up happening. So be very careful and have that strategy in place. Think about it. Keep it in mind. How do I make a backup plan? What do I do? Well, first of all, you need to determine what needs to be backed up. What is absolutely important and what needs to be backed up. This could vary from anything. Like if we look at that list of issues that could happen, well, you may have to back up your operating system because your operating system may have certain options in place and applications in place and settings in place that you don't want to have to go ahead, set up a new system and then rejig all of these settings. No, you need a backup of that. Then you have the question of, well, do I back up my entire database? Do I back up a part of it? always do a full backup of your database first. Always have one full backup. And then from there, you can go and decide, well, am I going to do more full backups or what am I going to do from here on out? But you need to determine what needs to be backed up. Then you can say, hey, okay, I need a full backup. That's the very first thing you need, a full backup. You need a backup of your entire database. And then you can go and decide, well, am I going to do more full backups? Is that going to be my strategy? Am I always going to do a full? That's a very good strategy. It's a potential. Then you could say, hey, let me do an incremental backup. And an incremental backup is basically saying, hey, here's my full backup. When you do your very first full backup, when you do an incremental backup, you're doing everything that changed since the last incremental backup. That's very important to note. It's everything that changed since the last incremental. If you had your very first full backup, it's everything that changed since the full backup. And then if you have your first incremental, well, if you do your second incremental, it's everything that changed since the first incremental. So that's what an incremental backup is. Then you have a differential backup. And what a differential backup is, it's always everything that changed since the first full backup. So you can already go and see, hey, this is going to be a bit faster than this is. Because this is always going to take a backup of everything that changed since that full backup. So when it comes to determining a strategy, speed is important. What's the fastest? If you're going to take, for instance, a full backup once a month, then an incremental backup will be fast because it's always going to do everything since the last incremental. If the last incremental was the first full backup, it's going to increment. So this is a good strategy if you're only taking a full backup, let's say once every 2, 3, 4 months. Then you can have all of your incrementals go over time. If you're taking a differential backup, well, you can already think, well, if it's since the last full backup, it depends on how heavy my database is. If you have 1 million users, taking a full backup is going to take a long time. But taking a differential backup, let's say, if the database had, for instance, 1 million records, and then we're taking a differential day by day, and suddenly you have a spike, and now there's 2 million records. That differential is always going to be based off of the last full backup, so you're going to have to back up 1 million records. So a differential always has to be based on the last full backup, meaning that you may want to take full backups more frequently to keep the differentials going fast. So there's different strategies in here, incremental being one of the fastest. And then you have transaction log. Transaction log is one of those things where on a day-to-day basis, transactions are happening. People are committing to the code base. Changes are happening. This is like a live snapshot of what happened that hour, that day, that whatever increment you take transaction logs at, which should be at a short interval. You want it maybe every 15, half an hour, maybe every hour, maybe every 2 hours. The more frequently you take these transaction logs, the less data you will lose, because they're basically a hot backup, and you have to have in place a policy for them. How long are you going to keep them? If your incremental happens every night, well, you only need to keep your transaction logs for that day, for instance. So a lot of factors go into this. And so when we look at it, a full backup is backup all the data. An incremental backup is backup since last incremental. A differential is backup since last full backup. And a transaction log is a backup of the database transactions. They all have different levels of freshness. A transaction log is the freshest. It has the most recent log of things that have happened. And you want to take these as often as possible, because based on how often you're going to take either an incremental, a differential, or a full, you may want to take transaction logs more or less frequently. You can already think, okay, if I'm taking a full backup once a month, for instance, and I'm not doing an incremental or differential, well, then I'm going to want to keep transaction logs all throughout that month, maybe on an hourly basis, maybe on every 15 minutes, whatever the case is, depending on how heavy your database load is. If you have a very heavy database load, maybe don't follow this strategy. All these strategies have a time and a place, and you have to decide them with a team. You have to think about it. But let's say you take a full backup once a month, and then you take transaction logs every 15 minutes of every hour of every day. Well, then you're going to keep transaction logs all throughout the month. Disaster strikes. Well, what do you do now? Well, then you have to run your full backup, and then you have to run transaction logs all throughout that month. So you're going to be running transactions. There's many transactions. So it's not as fast as, for instance, if you say, okay, I'm going to take a full backup once a month, and then I'm going to take incremental backups throughout the month. Well, now you have 30 or 31 incrementals, but if you took transaction logs every 15 minutes, you may have 2, 3, 400, depending on the amount of transactions that happened. So it's 30 incrementals happening versus 2, 300 transactions. And it really depends on how heavy these transactions are. Like an incremental is nothing more than the sum of a couple of transactions, but they're all handled differently, right? Like backing up and restoring data, it really depends on how heavy your database is and what you're trying to accomplish. And even with differentials, a differential is also great because, well, in that case, if you took a full backup once a month and you took a differential at the end of the month, disaster strikes, you only have to run one full backup and one differential. It really depends on how heavy your database is and how much risk you're willing to tolerate. Now, I read somewhere a statistic, and I'm not going to quote the exact number, but a large number of companies prefer to do just full backups. I once worked for a company where they would take an incremental every night at 3 a.m. And by the time you came into the office, that incremental will have finished, and they would keep tapes and tapes of the incrementals. And one time I actually did need to do disaster recovery, and I needed to run tapes throughout the system. And, from the history of data, they were still backing up on tapes. At the time, it was, I think, 2011 when I was doing this and running these tapes through the system. Really not a fun job, especially since business was halted that day in order to run these incrementals. So it's important to pick the right backup strategy. It's very, very important. Now, the next decision you need to make is, what's an appropriate way to back up? And what do we mean by this? What's the appropriate way? Well, when we talk about the appropriate way of backing up, it really becomes of that same question. Are we going to back up the operating system? Are we going to back up at the hardware level? Are we just going to back up the database itself? And so there's different layers to this. The appropriate way of backing up is very much determined by, well, what strategy are we going to follow? So, for instance, one strategy you could do is you could back up the operating system once a month. And then you could back up the full database once a month. And then you could do incremental backups of the database each day. And at the end of that month, you're going to back up the operating system again, and you're going to back up the database again in a logical way. So this is just us running, for instance, PG backup. This is what we call a logical backup. It's an appropriate backup. It's a way of doing a backup, but then think one layer lower. So when you think one layer lower, well, we're thinking about the hard drives. When we think about the hard drives, there are different appropriate ways to back up hard drives. You could take a full copy of a hard drive at the hardware level. You could copy section by section off of that hard drive and just create a clone of that hard drive at the hardware level. This is a very different type of backup. We're not running PG backup. We're not doing any of those software type related things. We're doing a hardware backup. We're saying this hard drive is a clone of this hard drive. So that's a different strategy. So you need to determine, hey, what's the appropriate way that we want to back up? Do we want to back up at the hardware level, at the software level? Both. A lot of companies determine a lot of different things. And when you're in the cloud, all of this changes. You have to think about it differently because you don't have anything on premise. You don't actually have any hardware. So you're taking a lot of logical backups at that point. And AWS is managing all of this hardware for you. It's a big advantage of the cloud because at that point, the vector of what you need to think about narrows, right? You don't need to think about everything, the hardware, the software, all of this stuff. You're just thinking about the logical database and how you're going to back up that data. You only think about the data at that point because AWS is managing all of this other hardcore stuff behind the scenes for you. Another thing that you need to think about, how frequently are you going to back up? How frequently? That's also what you put into your backup plan. How frequently are you going to back up? Are you going to do incrementals by day? Are you going to do differentials by day? Are you going to do differentials by week? It really depends also on how busy your database is and how frequent you get transactions. If you have a very small number of visitors, transactions, all of this stuff, you may be able to get away with a weekly differential or a weekly incremental even, or you could get away with something as much as bi-weekly. Maybe you need daily, maybe you need every 12 hours? Who knows? It really depends, but you need to decide how frequently you're going to do this and how volatile your data is. This is extremely important. Then once you have that narrowed down, well, then you have to look at, well, what is the general frequency of these types that I just showed you? What's the frequency of this full backup? Well, people tend to do it less often because it takes a long time and you're backing up all of the data. Incrementals happen more often because they're a backup since the last incremental. So they have a shorter amount of data that they need to increment against, whether it be daily or every 2 days, every 3 days. Differentials are backups since the last full backup. So they can become more heavy the more data that has changed over time. So you really need to determine if they can happen often. Once they start to take too long, if the backup is still running, for instance, a day later, well, that's not a good sign because the next backup should maybe start. It really depends on how much data is changing in your system. And then transaction logs, these need to happen a lot generally. You want to keep a backup of the transactions that happen because if disaster strikes in that minute, well, you want to be able to back up to the spot by the minute where the last transaction happened. And hopefully the rest of the system catches that failure at that time and stops the transactions from happening so that you don't lose a lot of data from that point forward. Fault tolerance is extremely important in a system, and systems vary so heavily. You have apps and you have servers and you have all these things that could potentially be writing transactions to your database. So it's important that all of these systems be able to be notified when disaster strikes so that they can take the appropriate action to be put, for instance, immediately in maintenance mode so that you don't lose a lot of transactions moving forward. Or even that if your app is able to hold on to that transaction until the database is back up. There's all kinds of strategies you can do, but the frequency of the backup is also important to note. Transaction logs can, for instance, happen every 15 minutes. How do I make a plan? The fourth key point, you need to decide where you're going to store your data. And in the cloud, it becomes self-evident that you're going to store them in a cloud instance. For instance, if you're on AWS, you may store it in S3, which is a simple storage solution. But if you're on-premise, you may have backup servers somewhere, or you may have backup servers in the cloud as well. It really depends, but you have to decide where you're going to store them, and it could be anywhere in the world. Last but not least, a very important point that not a lot of people tend to think about. What's our retention policy for the backup? Now, if you're in a regulated space like HIPAA regulated space or some other kind of medical or financial space, you may have to keep records for up to 10 years. So you need a retention policy for your backup. Now, if you're taking full backups and incrementals, well, you don't want to store full backups and incrementals for 10 years. You may end up taking a full backup once a year that's going to be held as a retention policy for 10 years somewhere, and every year you swap out that backup or you keep all of them. You keep them year by year. But the retention policy for your backup is basically how long am I going to keep this data? How long am I going to keep this backup? So it's important to think, well, how long do I need to store this for? Because storage may be cheap, but depending on how much data you need to store, it may be expensive. So it's important to take all of these things into account when creating a backup. You may think, okay, Mo, well, we talked a lot about all of the different aspects that need to go into backups and a backup plan and a disaster recovery plan and all of these things. How do I make a backup? That's a good question. Let's look at that. When it comes to backups, Postgres has the ability to backup and restore built into it. And when we talk about that ability, we're talking basically about creating an SQL dump. An SQL dump is nothing more than a text file that gets generated from a database that can contain either the schema, so the tables, or the schema in the data, or just the data. And when we generate this, well, we can create dump files in very different ways. We could export them as scripts that can be easily run against a different RDBMS and is readable, or we could create them as backup files, which aren't SQL commands, generally speaking, but Postgres can understand to back up and restore more quickly. And so when we talk about this, there are many different ways of creating that dump. and creating archives and all of those different things. Now, what we want to focus on is the ability for you to, in a simple way, be able to just back up your database. But that being said, we don't want to leave you without the ability to look into a tool more deeply. And so that's why we're going to point you towards PG Backrest. It is a reliable Postgres backup and restore tool that is aimed at simply and reliably creating a restoration solution. It's not shipped by default by Postgres, but it has the ability to do the incremental backups, the differential backups, all of those things that we talked about. It's very, very strong and capable as a backup solution. But for all intents and purposes, we want to give you the simplest and most straightforward way of backing up with Postgres. So let's go take a look at that. Now over here, we're in Valentina Studio. And in Valentina Studio, we are going to look at the simplest, easiest way of creating a backup in a visual way. Because running commands is cool and all, but any given software can run these commands for you. So we want to make it as easy and as visual as possible for you guys to be able to select and go through a graphical user interface, because it just makes things easier. It really does. So if we, for instance, look at our employees database, what would we do if we wanted to create a backup? Well, we could do something like create dump by right-clicking. So over here, when we create a dump, what we can see is that Valentina Studio gives us a lot of different options. And over here, you can see you can select an output format. You could select custom. You could say export it as a directory. You could say export it as Excel. You could even export it as JSON, which is a JavaScript notation. It's just an object notation. You could export it as SQL, as a zip file, as XML. There's many different ways. Now, the most common and the most used are either SQL, tar, or custom. And so let's go in SQL so that we can actually see what it's going to export, because we can read SQL. We're SQL masters at this point. And so then you have to decide, okay, what's going to be in my dump? What am I actually creating a backup of? Well, you could say structure only, which is going to take only the tables, their relationships, their constraints, all of those things. You could say structure and records, which is going to take both the create table statements, the constraint statements, and the data. It's also going to take the data. And then you could say, hey, only give me the data. So we're going to take structure and records, and we're going to continue here. And then we can see that you can select a dump utility. Since we're running Postgres 12, we're going to use backup utility that comes with Postgres 12. What we can see here is that we have additional options. We could include the create database statement so that we don't have to run it. We could do a clean before restore. It's going to add a clean script to a database that we're going to run against. We're going to add the create database statement though. And then when we say use insert commands, well, we could say use column inserts, which is going to specify the columns. It's going to say, well, can we use multiple row insert statement? So inserting multiple rows inside of one insert statement. And we could say, hey, do 250 rows per insert. Insert data in these increments. One insert statement inserts 250 rows, for instance. Then we could say, don't save the following. Don't save the owners of the database. Don't save the privileges. Don't save the table space. We don't want to necessarily add any of these. We could potentially drop the owner, which, as you know, the person who creates the data in the database and the tables is the owner. And then miscellaneous, you could set certain odd options that may or may not be required. So if we continue along this, well, it's going to say, I'm going to make this file in the documents, and it's going to be an SQL file. We're going to encode it as UTF-8. We don't want to encode it as anything else. And if we continue, now it's starting to dump and create the tables. As it dumps, what it's doing is it's basically generating create database, create tables, the constraints, it's doing the inserts. And once this is done, we can show it on the disk. And when we show it on the disk, what we can see over here is that we have an SQL file. So let's open that up. And what we're going to see in that SQL file is it's going to be a very large file. As you can see, it's gigantic. So we can see a Postgres dump. We dumped it from database version 12.3. It sets all of these different things, all of these obscure SQL commands just to make sure that the database mimics each other. We have our create database command with the template. It's going to do a connect. So it's actually going to connect to that database, and it's going to set some options on that database. It's going to create a custom type gender. It's going to set a table space. It's going to create the tables, as we said, in the public schema. And then if we go down, it's inserting records. It's inserting many, many records, and it's doing them by column name. And as you can see, like we specified, it's doing 250 per insert statement. And then the next insert statement starts, and so forward and so forth. And as we go along this route, what we can see here is that we have all of our data. All of our data is in this SQL document. You may think to yourself, this doesn't seem like a good way of backing up. And if you have an extremely, extremely large database, you don't want to store it all in this single text file. It would take forever to run. There are more efficient ways of backing up. That's why, for instance, we also do hardware backups, cloning hard drives and such as our first line of defense, for instance. There are many different ways, but as you can see, with Postgres, we have the ability to easily focus and export our database in a simple way. And as our database grows, our backup needs will change. And that's why we wanted to give you the ability to think about and orchestrate a backup plan if you need to, and look at different tooling. Because the Postgres tooling, although it can dump and it can create these nice files that have a copy of the database, it's not the most efficient way of backing up by any means. Differential, incremental, all of those different strategies we taught you, those are the things you need to focus on going forward. So with that, we know now how to back up in Postgres. So let's look at restoring. Time to restore our backup. As we said in the previous video, we created this backup that was an SQL file, and it had the create database command in it. It had all of the good hallmarks of being a file that we could first of all read. It had all of the data, it had all of the records, it had all of the constraints. Now, how do we restore it? And what I want to show you here is that the way you decide to create a backup influences the way that you're able to load it. So over here, we're in Valentina Studio, and you would say, hey, Valentina Studio can load a dump, right? Yes, it can. Let's see. You have two options. You can restore to a database, which we deleted employees, and we have our create database statement in there. So we don't want to restore to an existing database. So let's do it connection-based. And if we do a connection-based, now we're going to do SQL, and it knows that it needs structure and records. And it's already pointing to the employees file for which we created the backup. And we know it's UTF-8. And we're going to deselect, execute multiple dump statements. And we're going to start running. And already we can see we have an error. So why is this happening? Well, the way that you decide to create a dump really influences the way that you're able to restore that dump. Depending on how you created that dump, it may be easier for you to actually run commands in order to figure out how to restore. When we're restoring this database, as you can see, as it goes along, it may be successful, but we already have an error. So let's take a look at what that error is once this is complete. And it's processing queries, processing queries. This is a very visual way of looking at it, and it's very nice. And as we finish up here, what we're going to see is that we had a syntax error at the beginning, but all in all, it was done. So if we refresh here, we can see we have our employees database. And we can see that if we go inside of here, we have our public schema, but we have no tables. And we have no tables because the way that the SQL file was generated created that error at the beginning. So even though we ran all the queries and we did all the things, Valentina Studio was unable to process the script. Now, let's delete this physically again. And let's go take a look at how that would work if we were to do it from, for instance, let's say, terminal. So over here, we're in our terminal. And what we can see over here in our terminal is that we're able to run our PSQL command, and we can connect to a certain database. So let's connect to the Postgres database. And I don't need to use a user because it's by default going to log in. And if we do con info, we can see that because I'm using the Postgres app, I'm logged in as user education. That's all clear. Because we decided to generate our SQL script with a create database command, we could see that Valentina Studio hiccuped on the loading of the dump. Now, there's different ways of generating that dump in which Valentina Studio could potentially process that, or we could even go and fix the script. But let's just load the dump as it is, because this is not, generally speaking, how you would load a dump. Normally you would load a dump against the database and it would insert everything into it. Now we're running a script because that's what we generated is a script. So we have to point it to documents, and then we have to point it to employees, SQL, and now it's starting to insert. Now it's starting to run all of those good commands. And if we go up here, we can see that it's running many inserts, and I can't even scroll all the way to the bottom. We made it back. And as it goes through this, what you're going to see at the end is some tooling like Valentina Studio. Valentina Studio is built to process multiple database connections, MySQL, Postgres, all of these other providers. So the way that it decides to run commands may not necessarily be beneficial to the way that you want to back up and restore. So it's important to know, first of all, how are you backing up and how do you want to restore, and to use those tools directly. Graphical user interfaces, although easy to generate backups, can generally make it more difficult for you to be able to back up and restore. We would have to go and figure out a way for Valentina Studio, for instance, to generate a backup that it could properly restore. We would need to figure out how we need to adjust the script in order for it to be able to process it, because the script was built by PSQL to be run in command line, not to be run in Valentina Studio. So even though Valentina Studio can't process the script, it generated the correct script with the PSQL command. So now over here, what we can see is we did all our grants and alter tables and indexes and inserts. And if we go over here to Valentina Studio and we refresh, what we're going to see is we have our employees database back, and it has all of the tables. Even though we generated the right backup with Valentina Studio in an easy way, we can see it's easy to hiccup on the restoration part. Don't trust solely on tooling. Also know what you're backing up and how you're backing it up and how that may impact backup and restore. And with all of that being said, keep in mind that there are multiple strategies here, and they can become more and more complex as you go along. The purpose here isn't to make you back up and restore masters. These strategies are often driven by teams, operations, the corporate strategy, all different parties and all different architects coming together to think about these things, because it's extremely important. But if you're in a smaller scale and you're maintaining your own database, it's good to think about this, and it's good to know what options you have so you can dive deeper into them as you go along your SQL journey. And with that said, we were able to back up, we were able to restore, and we're good to go. We can even see that we have data in these tables. That's all on the up and up. Amazing. Transactions. Let's talk about transactions. Now, we've talked about a lot of different things when it comes to databases and the database management software. But one thing we haven't really gotten into is transactions and what exactly transactions are. Because that is an important concept when it comes to the database management software. At the end of the day, a database is a shared resource. So many users will access it concurrently. And so what this means is that when a lot of people are doing what we would call transactions, selects, updates, deletes, drops, creates, all of these things affect the state of the database. And since the database is shared, well, how do we make sure that when 5 or 6 or 7 people are accessing it, that the database stays consistent? That's where we look at transactions. Transactions are a unit of instructions. You see, with transactions, basically what we're trying to achieve is a unit of instructions that is going to run in isolation and not affect the state of the database until it's done. So with a transaction, we're looking, for instance, at a query. We've seen different types of queries, and queries can do different types of things. For instance, a select query. Well, that would be what we would consider a read transaction, because we're only reading. We're not really doing anything that will alter the state of the database. But nevertheless, we consider it a transaction because you are transacting with the database. You are trading something. You are giving it an instruction. It is giving you something back. But then we have things like update queries. and delete queries, and they altered the state of the database, and thus those transactions need to be warranted. If, for instance, 5 people came in and they started deleting a bunch of stuff, well, how do we make sure that if they're trying to delete the same stuff, that nothing happens? And so the concept of a transaction is to keep things consistent, right? How do we keep things consistent? This is the question we're trying to ask ourselves. And so with a transaction, we're basically saying, okay, anytime you do anything, we're going to start, quote unquote, the concept of a transaction. And whatever happens during that transaction stays in that transaction until you either decide that you want to commit it or roll it back. Database management software has a mechanism in place to manage transactions. So if you're doing 5, 6, 7, 8 transactions, if 5 or 6 people are doing update queries, they will all run in isolation within a transaction. And then it becomes a question of, if someone is going to commit those changes, then it becomes a question of, well, who's first? And that's where the database will get smart, and it will lock certain resources while an update is happening so that other transactions won't get into a weird state. It becomes very smart in this scenario. So when we look at the life cycle of a transaction, we see that a transaction will start. So you're running your query, right? And it goes into an active state. And so when it goes into an active state, well, then it's going to run itself. And so then it's going to execute itself. This is what we call partially committed. So when it's partially committed, it's executed itself. But if it fails for any reason, well, then it'll get aborted. So if it fails because something else is utilizing that resource, or it just failed because of a query mishap, then it will go into a failed state, it will be aborted, and the transaction will automatically be ended. But if you're partially committed, and let's say you like the state of whatever you did, an update, an insert, whatever, well, then you're going to commit that transaction. And then you'll end up right back at the end of the transaction, and you're at the end of it all. Let's take a look at what that would look like. So over here, I'm in my command prompt again. And as you can see, I am connected to the database employees as the user Postgres. And so what I wanted to show you here is basically a couple of things about transactions. And there are many, many, many things that you can say about transactions. It's a very, very deep topic that has a lot of nuance, a lot of architecture surrounding it. Every database management provider will handle transactions in different ways and have different concepts of how to manage all of this stream. But basically what it boils down to is when you run an update command, when you run an insert command, or when you run a select command even, all of these are inherently wrapped in a transaction. Your database management software is already wrapping it in a transaction for you because it knows that these are transactions. Now, granted, for select statements, you will never get into a state where it potentially may fail because it's a read-only transaction. But for updates and inserts and deletes and drops and all of that stuff, yes, you could definitely run into a scenario where an update or an insert will fail because another transaction is happening that's trying to do something with a record. And so the database management software tries to orchestrate this with transaction. And these commands are already wrapped in a transaction. But let's say you wanted to go through the process of creating your own transaction and running multiple things inside of that transaction other than one update statement. Well, what you would do is you would write begin with a semicolon. You have to use a semicolon. And when you begin, now you're in a transaction. Now I can't run begin again because what it'll say is, hey, there is already a transaction in progress. Don't create another one. We don't need this from you. You're already inside of one. So now that I'm inside this transaction, I could say, for instance, delete from employees where, and I could say the employee number is between 10,000 and 10,006 or 10,005. Let's go 10,005. And don't forget the semicolon. Every query in a transaction block has to be denoted with a semicolon so that it knows what it's doing. Okay, so now we've deleted 5. And if we select star from employees, well, then you can see that they're gone. We're starting at 10,006. So it's happened. This is what we would call a partially committed state. We're there, but we're not actually executing it just yet. We're in a partially committed state. It isn't really on the database just yet. And the way that I could prove this is if I went into a different terminal and I did PSQL Postgres U and I did select star from employees here. Let's up this a little bit more. What you're going to see happen here is I still have 10,001, 10,002. Now this is a different connection, right? I connected with Postgres, but I have a secondary connection. This is not the same session. This is a separate session inside of Postgres. So these are two separate sessions, even though I have the same user logged in. Now over here, you can see when I do my select, in this session where I'm in a transaction, I've deleted 5 records. But in this session over here where I'm just connected to the database, I don't have that transaction yet. Okay, so what would happen, let's say if I did a transaction here as well in this session, and I said, well, you know what? Also delete from employees, and let's say the same thing, where employee number, and then between 10,000 and 10,005. Okay, well, I'm trying to delete from employees where my employee number is between 10,000 and 10,005. But as you can see, it's hanging. Nothing is happening. Why? The resource over here is being locked. You see, I'm in a transaction over here, and the resource is being locked. So let's say that I, for instance, said over here, okay, I don't want to commit this. I'm going to roll this back. I don't want to do what I just did over here. Well, then I'll roll back, and then over here you can see, oh, it suddenly deleted 5. It suddenly deleted 5. Interesting. Now, what this is called is locking. So the resource was locked in this session over here, and when I rolled back, I basically said, hey, end this transaction. I don't want what's happening here. But over here, we were stuck on the delete. It wasn't executing, it was holding, and that signified to us that there was a lock on that resource at that second. Now, usually the resource wouldn't lock for that long. It would occur, and then maybe something would happen. Now, if we went back over here and we did another transaction block, and then we decided, let's do the same thing over here, let's do the delete again. Well, now this resource is not going to execute because this transaction is still in flux, so it's rolling. So if we were to commit this, so you could either write commit or you could write end. Well, now we've committed it. And if we go over here, it's going to say deleted 0 because the other transaction committed. So suddenly this one didn't have anything to delete, and we deleted 5 employees. So interestingly enough, the way that a database manager manages transactions is through wrapping things in these transaction blocks. And over here, I'm still in a transaction. If I said end, well, now I'm out of my transaction. I committed the changes. No changes actually happened. So these transaction blocks are the way that the database manager basically handles the ability for multiple sessions to go back and forth and try things out. And then if they roll back or if they commit, it may affect other transactions that may be trying to do the same thing or try to change the resource in a different way. So basically what it comes down to is in a transaction, when you're in this partially committed state, what you decide to do, whether you decide to commit or abort, really determines how other transactions are going to play out. As you saw, resources get locked while transactions are happening and they are in this partially committed state if you're trying to access or do something to the same resource. So as we said, update, delete commands, insert commands are inherently wrapped in a transaction. And while they're executing, other resources can't just go and partially commit against it either. You saw that with our delete, our other delete had to wait until the transaction ended. And so this comes down to the properties of a transaction. The properties of a transaction dictate why things happen this way. To maintain the integrity of a database, all transactions must obey the ACID properties. No, this is not some science experiment. We're not going to play with actual ACID. The ACID properties are an acronym, and they stand for, first of all, atomicity. You either execute the entirety of the transaction or none of it at all. The transaction has to happen entirely or none at all. So as you saw with our delete transaction, luckily it went through after the other transaction deleted 5 records, but it just would delete 0. But if that delete had failed for whatever reason, if the transaction contained like 6 or 7 or 8 queries inside of that transaction block, when you start a transaction block, you can run 6 or 7 queries in sequence and see the state of the database in a partially committed state without it affecting other sessions. But then when you want to end or commit the transaction, if any of the commands in that transaction fail, your entire transaction fails. So you have to execute it entirely or not at all. Now, the second, or the C in ACID, is each transaction should leave the database in a consistent state. It either has to commit or roll back. So if the transaction succeeds in whole, it's going to commit. Or if anything in the transaction fails, anything at all, any of the queries, it's going to roll back. So if your transaction fails, you may have to go and adjust your transaction in order for it to commit. So each transaction should leave the database in a consistent state. This is a hallmark of a transaction and should always happen this way. And that's the way that database management softwares implement transactions, so that they always leave the database in a consistent state. Then the I in ACID, isolation. Transactions should be executed in isolation from other transactions. Okay, this is important because when we look at transactions, they can't go and affect each other. They're both basically, think of it like them executing in 2 separate sandboxes. So you start a transaction, 2 sessions start a transaction. Well, now they both have access to the same database. But what's actually happening is they've created this little sandbox in which they can play. They can update, delete, insert, select. They can do all of these things within that transaction. And then when they decide, hey, I'm going to commit, well, that's when the database management software kicks in and says, well, this transaction is doing these things, so what you're doing may fail. And so the order in which transactions occur is very important. If transaction A happens before transaction B, transaction A may affect how transaction B will execute, because transaction B may trying to access the same resources. And so if they're trying to access the same resources, if transaction A goes first and it does something, it may cause something in transaction B to fail. So this one is going to roll back probably. But what we're trying to say here is that transaction A and transaction B started off with the same sandbox. But what happened in transaction A isn't known to transaction B until time of commit or rollback, because the database management software is going to say, hey, transaction A occurred, transaction A, B, C, D, E occurred, and now you're trying to do this transaction. Well, you started off way back when transaction A occurred, so let me see what happened in that meantime. And then it's going to say, hey, you can't execute this because something's going to fail because you're doing an insert or an update or something wrong in here that may fail because all these other transactions did something to that as well. So they happen in isolation from each other. They don't really know what each other is doing. But at the end of a transaction, the database management software is going to go and it's going to say, hey, I'm going to check out what you're doing. I may make something fail because all of these other transactions happen that may have touched the same resources that you touched. So isolation is important. They may start at the same begin point, depending on when the transactions occur. They're in isolation from each other. So transaction A and B are touching resources in a sandbox. And only when they decide to commit or roll back does it actually matter to the database management software. And it's going to orchestrate whether a transaction can commit or has to roll back. And then the D in ACID, durability. After the completion of a transaction, the changes in the database should persist. There is no halfway here. When your transaction commits, it is in the database. It has happened. It's done. There is no ability for it to be in a wonky state, a partially committed state. No, this is how it's going to be. So each transaction must in turn have durability. The completion of a transaction means that that data, that change that you did is persisted. It's persisted in the database and it's there. And so with all of this, foundationally, what we're looking at here is that unit of operation that we call transactions that is trying to make the database consistent, right? What we're trying to do here is follow those asset properties and make it so that when people operate against our database, that the database will never be in an inconsistent state. That's what you don't want to happen. You don't want 5 updates to occur and suddenly a record to be corrupted. You don't want it to be corrupted. That would be horrible. So that's why a transaction follows this sandbox approach and this begin to commit approach and locking the resource, right? It really wants to make sure that transactions happen in order and that they are ACID compliant and that whatever happens in that transaction is durable, that the database is durable. And there's so many more things that could go into transactions. But foundationally speaking, we're talking about that operational consistency of your database and your data. And transactions are just that unit of operation.